I'm Anil Kumar, and now let us discuss derivative of polynomials. In this particular video, we'll investigate the slope of the tangent line at x equals to 1 for some polynomials. Let me take a parent polynomial function. Let us say f of x is equals to x to the power of n. That is the parent polynomial function, where, as you know, n belongs to set of natural numbers, right? So that is the function. We'll consider the point where x is equals to 1. So if x is equals to 1, then f of 1 will be equals to 1 to the power of n, which will always be 1. That means the point which we are considering is 1, 1, right? So the polynomial could be of any degree n. We'll consider point 1, 1 on that polynomial and investigate the slope. Why slope? Slope represents derivative at that point for the polynomial, right? So we'll investigate slope at x equals to 1, and slope really means f dash of 1, right? Slope at 1, so the derivative on the graph of polynomial at x equals to 1, which could be represented as f dash 1, right? So the value of derivative at x equals to 1 gives us the slope at that particular point. So let's begin with simplest form, which is f of x equals to x, where n is 1. In that case, what happens? So let's consider the first function as, let me write this as in a different ink, f of x equals to x. So that is a straight line. So in this particular case, f dash of x will be equals to what? Derivative of x is 1, right? So it is equals to 1. So that is the derivative of this particular function. Now if I have the other function as cubic function or a square function, so let's increase the degrees one by one and see how the derivative changes. Now here you can always say that at 1, that means f dash at 1, if I write 1 here, this 1 will not change. It will remain 1 only, correct? Now let's take another derivative, and that is, this time let us consider the function as a square function, right? A parabola will be the graph for this, and derivative for this function is equals to 2 times x. So the derivative is 2 times x, and the value at 1, the point which we are considering, will be equals to 2, right? Let me take another ink for the third function, which will take as cubic function, and we can continue. So you can continue for different degrees of functions and make a table like this. What do you notice? That is the question. So the derivative is 3x squared, and the value of the function, the slope of the tangent line at x equals to 1, I should say, should be equal to 3 times 1 square, which is 3, right? So if I add one more to the list, and then we'll close at this point. So let us say f of x is x to the power of 4. In that case, f dash x will be equals to 4x to the power of 3, right? And the value of tangent, slope of tangent at 1 will be 4. So you can see a pattern growing, right? So from this pattern, you can make out that the derivative of a linear function is a constant, right? So derivative of a linear function is a constant. Derivative of a parabola, degree 2, is a linear function. Derivative of cubic function will be a parabola of degree 2, and derivative of quartic function is a cubic function. So what really happens is that, so we can write down this observation here. So what really happens as we find the derivative, so if we move from function f of x to its derivative, so let us say we have a function f of x, and then we find its derivative f dash x, then the degree decreases by 1. So then what happens is degree decreases by 1, right? So So that is what is happening, correct? So degree of derivative is 1 lower than degree of the function. You get the idea, right? So that is one thing which you clearly notice, right? Now let us also see what happens to the slope, right, at a particular point. Now, so this is the first part which we notice, and second part we notice about the slope at, we are considering at x equals to 1. What you can do is you can consider other points and see what happens, right? Slope steadily increases. Do you see that? So the slope increases as the degree increases, correct? So that is very important to understand, that if I have a graph of a cubic function, then the graph of a derivative of cubic function will be a quadratic function, correct? So that's the whole idea of considering this. So let me sketch the kind of figures which we have here, and then investigate further. So first function for us is a straight line, which we are saying is this is our function, right? So y equals to x. So this is our function y equals to x. Now in this particular case, the derivative of the function is 1, right? So the derivative f dash x is actually 1. Let us say this is 1 for us. So this is 1, correct? So this is y dash equals to, the value of y dash is equals to 1. And at a particular point which is 1, you can see the slope is 1. So this point is 1. And slope for a line will always be same, correct? Now if I consider a parabola, so x equals to 1 will also give me a point 1, and parabola, as you know, will be a function kind of like this, right? So we have a function like this. Now for this parabola, the equation of the derivative is 2x. Do you see that? So 2 times x is a linear line going through 0, but with a slope of 2, right? So kind of it goes like from, if this is 1, that will be 2, right? So and going through this. So the derivative of this function was kind of like this. Do you see that? So this is f dash of 2x. So that is the derivative of parabola. Do you see that? So so this is for parabola. So what you see here is that the slope increases, right? If you consider the point 1, of course it has to be 2, so it will be parallel to this, so it will go through here. So at point 1, the slope of this line will be kind of like this. So that is the slope at the given point for the second function. What you notice is that the slope for the first line goes through the origin. Second, the x-intercepts moves right, correct? Now let's move in to the cubic function. Now in case of a cubic function, if you sketch that function, well, at 1 the point is going to be 1 itself, but it's going to be kind of, let's say a cubic function is kind of like this, right? So let us say that is a cubic function. In that case, we know that the derivative is 3x squared. So it's a parabola which will be steeper than this. So it is kind of, the derivative is kind of like this. Do you see that? It is steeper, right? So it is kind of steeper. And the derivative of this particular function at x equals to 1 will be line with the slope 3. So the slope is 3 for us, correct? So in this case, we have f dash at 1 equals to 3, correct? So this is for the cubic function. So what you clearly notice is that the slope increases, and what also you notice here is the x-intercept moves away, right? So the movement of x-intercept, which was at 0 earlier, moves away towards the right. Now as the degree goes higher and higher, now the question for you is that if the degree of this function is very high, let us say that if my let's go through this, and if x is, let's say, to the power of 10, in that case where will the x-intercept be and how steep the line will be. Can you write down that at that particular point, right? So you'll see that becomes steeper and steeper as the degree goes higher and higher, right? So as what you notice here is that as n increases, right? So as n approaches large amount, let's say infinity, right? So what happens? The slope becomes infinitely vertical, right? So f dash x becomes vertical, right? So it becomes steeper. Do you see that? So that is what you notice whenever you're working on derivatives of polynomials. I hope this video gives you a good idea of what happens to the derivatives for a polynomial functions and how from a graph you can figure out which graph represents derivative and which represents the original function. I hope that helps. Thank you and all the best.